My name is Calvin Patmore. I'm a master's student over at Boston University in the United States. I work, the research is done over at the Center for Space Physics, which is at Boston University. And I'm here to talk about the characterization and design of a solar panel hinge that we designed specifically for the 6U satellite called Andesite, but that we also hope to use for future satellites at BU for Boston University as well. Things to kind of keep in mind when we do, we're a small university program, like a lot of the university programs, we have pretty limited funding. So we kind of try to do whatever kind of unique and innovative things we can think of to make the satellite one much more efficient, much less risky, much more efficient to build as far as time and money. Before I move on, I want to acknowledge my lab mate and who's also helped me with a lot of the work on this, Alvaro Zietti. He's been kind of working on this hinge design even before I started with it. So moving on, here's just a brief outline. I'm going to discuss a little bit of the Andesite mission. So give you guys kind of an idea. It's a pretty unique satellite project. And then I'll get into the solar panel hinge design and how we just intend to do the testing for it. So Andesite stands for the Ad Hoc Network Demonstration for Extended Satellite-Based Inquiry and Other Team Endeavors. I did not come up with that acronym. It investigates so what we want to do with it is investigate the filamentary structures of the Birkeland currents. And specifically, basically get kind of so not just what's happening at one point, but what's happening over a large span of the current. And we want to do that with a network-based satellite approach, which we've kind of seen a lot of talks on before. Here's the kind of the con-ops of Andesite and how we intend to measure these Birkeland currents. Is we're going to launch up a 6U satellite, or 6U CubeSat, and launch it out of the standardized canisterized satellite deployer. And once we finish detumbling, get the kind of the housekeeping up and running, the Andesite will orient itself and deploy these small sensor nodes, which we call TOS, and we'll deploy them 2 at a time throughout the orbit to try to achieve 2 to 5 kilometer separation. And as they pass through the Birkeland region or the polar regions, with the GPS, they'll turn on, collect the 3-axis magnetometer data, timestamp it, and send it back to the mule. What's interesting and what's kind of unique about the way we're doing this is instead of just sending it to the ground, we actually have a true wireless network where the farthest sensor node will send it to the next closest node and kind of throughput the data until it gets to the mule, which will then downlink that data to a ground station through the Globalstar network. So, kind of generally, or I guess kind of taking a step back, the Andesite wasn't the first satellite Fuse worked on. Before, it was a 27U, more of a small satellite, and that satellite went through a full, had to develop its own hinge solar panel deployment system. So yeah, that satellite had to develop its own deployment system. So a lot of those team members moved over to the Andesite team and said, well heck, instead of coming up with kind of a new system that we have to recalibrate, recharacterize, retest, can we come up with something that's a little more general that we can then reconfigure for future satellites? So we don't have to do the extensive environmental testing every time a new configuration is going. So kind of the broad solar panel requirements is more of a it needs to be self-actuating, self-guiding, and self-locking. And the torsion spring pin latch concept kind of derives directly out of that. And non-surprisingly, it's one of the most common springs or deployment systems found on CubeSat. And you can even find these as COTS packages or commercial off-the-shelf packages from Pumpkin, Honeywell, and I know the likes of Clyde Space and Dom Aerospace also make full solar panel deployment systems using these packages or using this type of hinge. Unfortunately, these packages also are quite expensive because of the extensive testing that has to go into such, such a kind of a complex hinge using 3 different moving parts. And that's why a lot of the larger satellites use more, what we found, more of a kind of a solid state approach, which they use tape measure steel, which is essentially they go get tape measures from hardware stores and characterize them and then select the one that fits their application or their solar panel size the most. We've found a lot of good insight of this approach or this type of system from projects like Maeva, and also papers authored, single authored or co-authored from Sefin and Pellegrino. So kind of summarizing those 2 hinges, though, they do have their faults. Like I mentioned before, the complexity of the pin, torsion spring, and latch hinge has several thermal effects such as galling and cold welding, as well as a moving friction that's inherent to the design. These can cause a failure to deploy, which would be detrimental or could be detrimental to the science mission or the mission of the satellite. The tape measure steel is good because it essentially has a guaranteed deployment rate. There's nothing really holding it back from deploying. However, you do have to characterize, you can't just go buy when you go buy aluminum, you can go buy 6061 aluminum or a very specific alloy or steel. But when it comes to these tape measures, you're very limited to the whatever you find off the shelf. And like I said before, you have to characterize that for your specific situation. They all kind of then share the same problem as each system ends up being somewhat unique for its current specific application. It can't be readily scaled, and therefore you have to go through a full individual qualification of each one. I wanted to make one more point though on the tape measure. I know we heard earlier of a way to actually build or make your own tape measure with the press, using a press and heat treating it. And we actually thought about this method ourselves, but it came down to a university environment is generally not equipped to that kind of metal work. So we wanted to come up with something that's much simpler and accessible to especially universities. So we took a lot of inspiration from the tape measure type hinge system, and we essentially came up with orienting 2 pieces of spring steel. We took 2 pieces of spring steel, offset them from each other, and used the kind of the internal, the inherent stiffness of that offset to drive the hinge. So here's 2 pictures. I didn't have a scale, but I have a kind of a size. I don't know if everyone can see it, but that's kind of the size that we're dealing with. So it's not, so everyone has an idea of what when they see these pictures. So both of these pictures up here, the one on the right is actually the actual hinge that we're using on the andesite structure. And a key component is all these items were built from, we could build essentially 30 or 10 plus of these hinges with no more than $30 worth of aluminum. And the machine time, or the machining was designed and run all by students on CNC. So it's very accessible to the university environment. It doesn't require any professional machining. Moving on, so after we kind of came up with this idea, we wanted to do a dynamic characterization of it. And the main reason for this is so we can give it to our attitude control team, and they can plug in the response or the dynamic properties of the system and see how it affects their attitude control. And then we can tune the hinge, either make it less stiff or dampen sooner based on their input of how it affects the attitude control. So to do this, we decided to measure 4 different hinge configurations. So we took a 0 degree, which is our control, which ends up being very similar to an ideal spring system. And then we have 3 different offsets, the 15 degree, 30, and a 45 degree offset. And we also adjusted the thickness on a couple of these. So for this steel right here, it's 5/1000ths of an inch, which I think it's 0.12 millimeters or 0.13. I apologize for not knowing the exact. Anyways, and then we also moved it up to 7/1000ths of an inch. So we have a different thickness and a different offset as well. So and then what we want to do with the dynamic test, or here's the dynamic test. What we want to do is test those different configurations in a microgravity environment. So in this past August, we flew the test rig, which is in the bottom left picture, on a NASA microgravity campaign out of the Johnson Flight Center in Houston, Texas. The right picture is an example of a 1U setup. So what we have is we measured a 1U, a 3U, and a 6U solar panel, as we feel the most commonly used solar panel sizes, and or change these spring offsets or housing offsets for the different weights. And we collected position versus time information using a high-speed camera, and also a strain versus time, which is using a strain sensor, which would be the force output of the solar panel on the satellite structure. And the reason we have two of these is so that we can actually line them up and see if there's, see if the data or the correlation matches. So here's an example of the 3U 15-degree deployment. And this is a sequence, so I just basically overlaid the images we pulled from the high-speed camera, just kind of an idea of the sequence. And the first plot on the right is the actual strain, or the actual position versus time plot or data. And that's actually not filtered, so we got really good data out of this measurement system. The next two plots is the velocity and the acceleration of the system. And the combination of those three plots leads us can be used to then model, come up with a dynamic or analytical model of the system. So for the 0 degree, the most basic model is the linear mass spring dash pot differential equation. And so we basically use a least squares fit method and solve for the spring constant and the spring, or the damping coefficient, the spring constant, and this is the output or the model we received. So it correlates really nicely to the data. However, when we move to our system, or the 3U and the 6, or the 15 and 30 degree, we get a much nonlinear system. And you can see there's two nonlinears in asymmetric damping nonlinearity, which you can see the dampening cone does not match the bottom or top. And also the natural frequency changes over time as the spring begins to dampen. So what we're basically trying to do now is come up or tune the ideal system with different parameters, with more nonlinear parameters, to hopefully come up with a system that would work for all the different configurations. So here's an example of one system that works, but we need to do a lot more modeling and figure out what these actual constants do. So just to finalize or basically discuss our next steps is we want to figure out, one, find a model that works for all of them, and then two, use a static test, which is kind of shown on the right in a render, to figure out what these actual different nonlinear constants do in nonlinear terms. And then also we need to do is measure analyze the plastic deformation, because there is some plastic deformation when you open and close these springs multiple times, and also do some thermal testing. And thank you. Any questions?
Thanks very much. All right. Any questions?
Yeah. Check the deployment with zero-G device. Did you check the deployment of the paddle with the zero-G device? You want to simulate the situation in space where there's no gravity.
Yeah. So we tested it in zero gravity on a zero gravity flight.
Time for another quick question? No? All right. Thanks very much.